What's up, everyone? Today we're going to do an interesting problem where we are going to implement a priority queue. And so this is going to be a little bit different than a lot of the problems that we normally do, because this is not going to be one where we're going to spend a lot of time trying to work out how to solve it. This is actually something where, with all of the other standard data structures and some of the most common algorithms, you actually want to know how to do this when you go into your interview. So you want to know how to implement a binary heap and how to float up or bubble up and bubble down the values when you insert and remove values from your heap. But we're still going to talk through it, and we're going to talk through how to do it, and we'll talk through how to approach this as an interview question. So the first thing we want to do, as always, is that we want to ask any questions we might have. So the first thing that is worth asking here is, do we have to do generics, or can we just use type like an integer or something? And so in this case, I'm just going to implement this with integers. You could do it with generics, and it wouldn't be that much more difficult, but it would be enough more effort that I don't really want to deal with it. So I'm just going to do it with integers. And another question that's sort of related that we might want to ask is this going to be a min priority queue or a max priority queue? And the difference here is that with a min priority queue, it's sorted with the minimum value at the top. And with a max priority queue, it's sorted with the max value at the top. So when you pop the value, you're either popping the minimum value or the maximum value. And in this case, I'm just going to do a max priority queue, but it really doesn't change any of the logic of the problem, and you could do it either way. You could just flip the conditions that we're going to use to bubble up and bubble down, and that would be totally fine. Other questions you might want to ask is, do we want to have this be a fixed size or not? When we implement heaps, usually we implement our heap using an array, and so we're going to want to, in that case, it's going to have a fixed size, right? And so we want to know whether we need to be able to resize the array, or if we want to back our priority queue with an array list instead, or what we want to do. So in this case, I'm going to assume that the array is going to be, that I'm going to use a fixed size array to back my priority queue. And so the size is going to be fixed, which means that I'm going to have to check if it's empty or full before popping and pushing. But it's going to make it a little bit easier to do the backend. So let's go ahead and talk about how we're going to actually implement this. And we're going to implement this using, as I said, a binary heap. And to create the binary heap, we're going to do that using an array. So we're going to, let's say that we're going to create a binary, let's make it size 7, our binary heap. So when we insert items, we're basically going to insert them at the next available space in our heap. And so for the first item that we put in, and I'm also going to represent this as a tree simultaneously so that we can sort of see what we're doing here. Let's say I'm going to put in 4 as my first element. Then I'm going to put it in here. And that's all I have to do because that's the first element. And I'm going to keep track of I'm going to keep a size pointer or something, or I'm going to store the size of the array so that I know where the end of the array is. So I'm going to represent that just by showing this pointer here that's going to point to the last valid element of the array. And so now let's say I want to put in another value. I'm going to, in this case, let's put in a value that is greater. So we're going to have to bubble it up to the top. So we always put the value in the next available space. And so I'm going to put in this value 6 here. And with the array, it would look like this. And then to bubble to the top, you just look at the parent and see if the current value is greater than the parent. And if it's greater than the parent, you swap them. So I'm going to swap these two in this case, and I get this. And then the same is going to be true here. So we now have this. And that obviously took linear time based on the height of the tree. And so that's O of log n time based on the entire size of the tree. And so we'll add another value. Let's say we add 3 here, and we incremented this pointer before. We'll add 3. We don't have to do anything because 3 is smaller than the parent. And now we can add one more value. We'll add, let's say, we can add a bigger value. So let's add 8. And so we put 8 in here. And we see that, oh, well, 8 is greater than 4. So we're going to swap 8 and 4. 8 and 4. And then 8 is greater than 6. So we're going to swap them again. So we're going to get 6 and we're going to get 8. And now, we could continue this. We could add, let's just add one more smaller value. We could even add, let's say we add 7 just to make it a little more interesting. So we'll stop somewhere in the middle. We'll add 7 here. We put 7 on the end, and then we have to swap it with the 6. So, oops, we need to swap these here. And this is now pointing over to the 7. So we're going to swap the 7 with the 6. So 6 and 7. But now 7 is less than 8. And so we don't actually have to do anything. So hopefully that makes sense how we're inserting elements. Now we need to remove an element too. So let's remove the 8. We're always going to remove this top element or the first element in the array because that's how we're sorting it, right? So that's going to always be the top element. And so we're going to remove 8. And then what we do is we take the very last element, which in this case is 6, and we replace the original top element with that. So we're going to take 6 and put it here, and we're going to decrement the size of our list, or our heap. And now we have to bubble down the 6. Right, we have to move it back down into its appropriate place. And so we'll actually just find the greater of the two children and then swap it with that. So in this case, that's 7. So 7, now we took the greater of the two second level children, which is going to make the largest element now be at the root again. And then we swap it with the 6. And then we would continue to do this as long as we need to. And that's all there is to doing that. And in this case, we didn't actually have to delete this 6 from the array because we're keeping track of what the end of the array is. So we're not too worried about that. So hopefully that all made sense. That's going to take O of n log n time to both insert and remove items from our queue because we're always doing it based off of the height of the tree, right? We never have to make more moves than the height of the tree. And we never have to and we don't ever know that it's going to only take constant time. So let's go and actually code this up now. We're going to create a class because this is actually going to be an object. So I'll call it priority queue. And I believe that there is actually a priority queue type in Java already. So if you were doing this yourself, you'd have to be careful that you weren't also importing that or you could get a conflict. But like if you were actually coding this up, but we don't need to worry about it right now. So in our object, we're going to have the array that's actually backing it, and we're going to have the size so that we know where the end of the array is. So I'll have a int heap and int size. And now let's create a constructor. So our constructor can take in a size of the array so that we actually know, or the size of the queue, I guess, so that we know how big to make our backing array. So we'll just do public priority queue. It's going to take in an int max size. And then all we have to do is instantiate the array and set the size value. So we'll say that heap equals new int max size, and size in this case is going to be equal to 0, right? Because we don't have any elements in our queue yet. So now let's go ahead and we'll implement the first method, which I'm going to implement push first, and then I'm going to implement pop afterwards. So we'll have this public void push. It's going to take in a value that we're actually going to push, and we're returning void because, you could in theory return the total size of the priority queue now that you added this element, or you could return some value, but we're not going to return anything. You could also what I'm going to do is if the priority queue is full, I'm going to throw an error. But instead, what you could do is just return a flag. So you could return a Boolean true or false, which would say true if it got put in the queue or false if the queue was full. And so you didn't put the value in the queue at all. So it's up to you how you want to do it, and you can ask your interviewer about that. But for starters, I'm going to check if the queue is full. So if size equals heap.length, then I'm going to throw new illegal state exception. And in this case, what I'm doing is I'm actually going to say that the size is going to be, so the size is basically like the index of the last element plus 1, because when the size is going to start as 0, and then when I add an element, it's going to be in the 0th position of the array, but the size of the array is going to be 1. So that's how we get this heap is equal to, the length is equal to the size. So now what I'm going to do is I need to get, when I'm pushing, I need to figure out what the position is that I need to push the value into initially. So initially I'm going to push it into the last position, or the first available open position. And so that's going to be size in this case. So I'm going to create a new variable called pose or position, and I'm going to set that equal to size. And then I'm going to go ahead and set put my value into the heap. Because the first thing we want to do is just put our value in, equals value. Now we need to do the actual, in this case, bubbling up into the right position. And so to do that, I'm going to do a while loop, and I'm going to say we're basically moving from position up to 0. Like the minimum value of position could be 0, because that would mean that we were at the root of the tree. So I'm going to say while position is greater than 0, and then I'm going to bubble up. So while we're not in the top position, still look up one level and see if we can move into the top position. So now we need to figure out what the parent is of this, because we want to look at the parent and see if the parent is smaller than the current value. And if it is, we're going to swap them. And so how do we get the parent here? In this case, when we look at our array, we see that the children of 0 are of index 0 are 1 and 2. The children of index 1 are going to be, let's see, 3 and 4. The children of index 2 are going to be 5 and 6. And this pattern will continue ad infinitum. And so we can compute what the children are for a given index, but we can also compute what the parent is for a given index, because we can simply do the reverse. And so in this case, we see that, well, 0 is the parent for 1 and 2. And so if we subtracted 1 and then divided by 2, then we would get the parent, right? So we could, or alternatively, if we increment the position by 1, then we can get 2 and 3, and then doing integer division and dividing those both by 2 will get us to 1, and then subtracting 1. So we could do it either way, but I think that the simplest is in this case going to be int. So int parent is going to be equal to position plus 1 divided by 2 minus 1. And so again, you could do this in multiple different ways. You can obviously rearrange this equation however you want, but that's going to give us the parent for any given node. So it's going to give us the index of the parent for any given other index. And so now that we have the parent, we can compare with the parent. So we're just going to say in this case, if heap parent is greater than or equal to, so I'm going to just first say if it's greater than or equal, then I'm just going to break out because we're done and we don't need to do anything more. And if it's otherwise, on the flip side, if it's less, then we will need to continue, then we need to swap them and continue our while loop. So we're just going to say is less than heap position, then we're going to break. And otherwise, I'm going to actually implement a method to swap the indices as well. So I'm just going to pass in 2 indices and the array and just say swap them, because I'm going to do it multiple times, so it's easier to have it in one line. But I'll do this after the fact, but we're just going to have a void method here that's going to be swap indices, and it's going to take in an array int I and int j, and we'll implement this later. But what we're going to do if we do need to move up, if we do need to bubble it up another level, we're going to swap the indices. So we're going to say swap indices parent, and well, actually, so in this case we don't actually need to pass in the array at all, right? Because we have that as an object variable. And so we're going to, this swap indices can be specific to this for the heap, and then in that case we can just say parent and position. And then now that we've swapped them, we have a new position, and so we're going to say position equals parent, and that way we know that our position is going to continually decrease over time, and we're eventually going to either break out or our while loop is going to terminate. And so that way we know that. And then of course at the very end we just added another element, and so we need to increment our size. And we could increment our size somewhere else too, as long as we get the position first, but it's just, I think it's easier to increment it at the end after everything is done. So let's quickly implement this swap indices while we have it. All we need to do is just a standard. We're going to create a temporary variable, so int temp equals heap I, then heap I equals heap j, and heap j equals temp. So like we're not really doing anything there, but it's just like having that as its own thing is going to make it makes this code here simpler. And we're going to use it again for the popping as well. So now let's implement the pop. We're going to have a public, so this is actually going to return an integer, right? Because we need to return the value that we're popping. So it's going to be public int pop, and it's not going to take in any values. And again, the first thing that we need to do is make sure that that it's a valid function. So if our priority queue is empty in this case, then we aren't able to pop anything. So I'm going to return the same error as before. So if size in this case equals 0, then I'm going to throw a new illegal state exception. And with picking the errors too, there are sort of proper errors to do for Java, but it doesn't really matter too much in the context of the interview. It's just if you pick something that's within reason, it's fine. You can even define your own exception if you want to. It's not really a big deal one way or the other. So now that we know that we have there is a value, we can get the value right now. We can get the value immediately because it's just the first element in our array. But then we still need to replace it with a new element and bubble that down. So we're going to get the value initially, but then there's still more work to do. So I'm going to say int to return is going to be our max values. So that's going to be heap 0. And then now I need to move the end of the array to the beginning. And so I'm going to say heap 0 equals heap size minus 1. So now we've moved that value to the beginning, and we just need to do the reverse of what we did before, where we bubbled it up. In this case, we want to bubble down. So I'm going to say our position in this case is going to start at 0, and then for our while loop we need to think a little bit more carefully. So we know that we don't want our position to be greater than a certain value, but what we really want is our position is representing the current node that we're going to swap with the children of that node, right? So we're starting at 0, and then we're going to say, is the node here less than its 2 children? And if it is, we're going to swap. And so we don't ever actually want to go past where the value is going to have children in our array. So if we went more than halfway through our array, then the value wouldn't have children, and so there would be nothing for us to swap it with anyway. And therefore we can actually do while position is less than size minus size divided by 2. And that's because the children, as we saw from this formula here, we're basically getting that the children are a multiple of 2 away from the parent. And so parent times 2 is going to be the children, roughly. I mean, within 1 or 2. And so we don't want to go past that, because then there will be nothing for us to swap with. So there's no point. But hopefully that made sense. But now what we're going to do is we want to figure out what the children are. And in this case, we have 2 children that we have to choose from. So I'm going to say int left child. And we're going to do something similar to what we did before. Remember, we had this. So in this case, I can just say that the left child is going to be 0 times 2 plus 1. And then 1 times 2 is 2 plus 1. 2 times 2 plus 1. It's just the opposite of what we were doing before. So the left child is equal to position times 2 plus 1. And then, of course, the right child is going to be equal to the left child plus 1. But so here's where it gets a little bit tricky. And the thing that gets a little bit tricky is that it's possible for us to have a left child but not to have a right child. So even if the node does have children, it doesn't necessarily have 2 children. And so what we're going to do is just check the size of our array or the size of our queue, just to make sure that it actually works. So because what I want to do is I want to compare my current node to both of its children if it has 2 children, but otherwise I only want to compare with the left child. So I'm going to start by comparing it with the right child, or I'm going to start by checking that the right child is an actual child and exists, and then I'm going to compare the 2 values to see which is greater. So, and hopefully that'll make sense when you see the code. We're going to say if right child is less than size, so if we need to worry about the right child at all, and heap left child is less than heap right child, then in this case, we're going to swap with the right child. And so the reason for that is we want to swap with the greater of the 2 children. So if there is a right child and the right child is greater than the left child, then we want to swap with the right child. And otherwise, we just want to compare our current value with, and then we also do want to check that the right child is greater than our current value. But then otherwise, we're just going to we can only swap with the left value. So we're going to say if heap position is greater than or equal to heap right child, then we're going to break, because we don't need to swap. And otherwise, we're going to swap the indices with position and right child. And then we need to update position. So position equals right child. And then the alternative here is just we're going to do the reverse on the left side. So we're going to say if heap position is greater than or equal to heap left child, then we break. And otherwise we swap the indices. And then we say that position equals left child. And then finally, at the end, we need to decrement the size, and we need to return our value. So that's what our code looked like for popping, and hopefully that made sense. It gets a little bit tricky, I think, with the size divided by 2, the whole deal with the size divided by 2, and also making sure that the right child is in bounds. And you could potentially do this a different way by starting with the 2 children and then going from there. So starting with the children and then looking up to the parent, and so you would iterate to the end. But I think that this makes a little more sense in terms of logically thinking about it. So if this code makes sense, then I think that this is a preferable way to do it. And so let's just go through a quick example. We'll just go through a quick example and we'll push a couple elements and pop a couple elements, just to make sure that it does what it's supposed to. So let's consider again what we had here. We can just do, let's pop them in, and we can just do, let's do 3, 4, 5, and 6. And we're going to push these one at a time. So we'll implement this, and we can just say size 6. It doesn't really matter. We're going to say size equals 0. And now we're going to push 3. So we say that the heap.length is not equal to size. And so position equals size, which is 0. And then heap position 0 equals 3. And then the parent is, so in this case, we're already at the top. So position is not greater than 0, and so we increment the size by 1. Now we'll push 4. We go ahead and we say that we push that into position 1. So we push 4. And now we say position is greater than 0. Parent is equal to 1 plus 1, which is 2. Divided by 2 is 1. Minus 1 is 0. So the parent is 3. Then if heap parent, which is 3, is greater than or equal to heap position, which is 4, which it's not, then break. And then otherwise, we swap indices. And so we just say, I'm going to assume that this is correct. You could test it if you wanted to, but it's a pretty simple function. We're going to swap the 2. And so that means that we're going to swap 4 and 3. And then position equals parent, which is 0. And now our position is not greater than 0, so we break and we increment the size by 1. We'll do this, we can just do this one more time, probably is sufficient. We'll go ahead and push on. We're going to put the 5 at position 2, and then we're going to position is greater than 0. 2 plus 1 is 2, is 3. Divided by 2 is 1, because we're doing integer division, which is important to keep in mind. Minus 1 is 0, so we get 0 is the parent. Then 4 is not greater than or equal to 5, so we swap them. And we end up with this. So now let's come down and we'll pop a couple. So we start with, we'll say, first check the size, and of course the size is not 0. And then we're going to get this to return value, which is going to be 5. And then, of course, we have to go through the rest of actually bubbling our new value down. So we'll take the 4 and move it to the position where the 5 was. And now, while position is less than size over 2, so size over 2 in this case is 1. So while position is less than 1, then we're going to say left child, so left child equals position, which is 0 times 2, which is 0 plus 1 is 1, and right child equals 2. And we're going to say if right child is less than size. So in this case, right child is less than size. But actually, we'll see here, this is a problem, because we actually have already, our right child is this one, and we've actually already moved that. And so this is no longer valid. And so to fix this, we're actually not decrementing size until the end, but what we probably want to do instead is we can decrement the size here before we actually do this. So now if we try this again, we'll get the size is equal to 2. So we get that right child is less than size, and doesn't matter, so we'll skip. And then heap position is 4, which is 0, and then heap left child is 3, so we break, and it is greater, so we break and don't do anything. And then we return the 5, and now let's try this one more time. We're gonna come here, the size is still not 0, to return is going to be equal to 4, because it's the top, and then heap 0 equals heap size minus 1, so heap 1, which is 3. So we put the 3 there, we decrement size, so size is now equal to 1. Now when we come down here, we say while position is less than size over 2, and so position is 0, size divided by 2 is also going to be 0, which is good because we don't actually want to do anything, because now, since our size is 1, this is the only valid element in our array. We don't actually want to consider any of the other elements. So from there, we can just go and we will not do anything, and we're just going to return our 4 here, which is what we expect. And then if we call this one more time, we would just get this 0 value, and then we'd also get, we should confirm that we're not getting an index out of bounds error. Size minus 1 would be 0, and so we would just replace it with itself, and then decrement the size to be 0, and then position is not less than 0, so we would, is not less than 0, so we would return that, and then in future calls, if we didn't push anything, we would get this illegal state exception. So that's all there is to this. It's kind of an involved problem, but hopefully that all made sense. This is definitely something that's worth understanding, at least understanding how to implement a heap using an array, because it's a very common thing that comes up, and there are a lot of other problems that can be based off of this sort of concept. So it's a good thing to know. And otherwise, I will see you guys again soon.